on this website for more activities. It's a very active group of research. So the next talk is a bit of an outlier because it's not on deep learning, but I guess it's always good to have more theoretical talk to introduce us to new ideas. So it's a talk by Govind Menon from Bonn University, and he will explain how to introduce information theory to prove the Nash embedding theorem.
I'd like to begin by thanking the organizers for providing me with the opportunity to speak with you. My name is Govind Menon. I'm a mathematician at Brown University. The title of my talk today is Information Theory and the Embedding Problem for Reimannian Manifolds. I'd like to explain to you what this subject is about in the brief period of time that I have. So I'd like to introduce you to the Nash embedding theorems. These are classical results in mathematics from the 1950s, but there are several open questions that remain. So I would like to explain to you what the kind of recent stimuli has been for looking at these questions again, and to introduce you to certain new models that I'm creating and a certain way of thinking about these problems that I've been developing over the past few years. I would like to first state precisely what the embedding problem is for Riemannian manifolds. Our assumption is that we are given a manifold of n dimensions along with a metric on it. An embedding of this manifold, an isometric embedding, is a mapping from the manifold into an ambient space, which I'm going to denote by RQ, that solves the following partial differential equation. So this is a nonlinear, a quadratically nonlinear PDE. It's somewhat easier, at least for me, to think about it visually as an equation of this nature. So the thing to observe is that it's a matrix equation. G is a metric, so at every single point, what we have is a positive, is a symmetric positive definite matrix. So there are n times n plus 1 over 2 equations corresponding to the upper triangular region of that square. And our game over here is to find the solution to this PDE. So that's the narrow technical way of thinking about it, but what's really going on conceptually is a fundamental investigation of the nature of space. A manifold is a space that topologically looks like, locally looks like Euclidean space. And what we're asking over here is whether the set of all possible manifolds can be realized with a very concrete description that is familiar to us from the work in the 19th century. So Nash's work should be seen as kind of a new way of thinking about the nature of space. And that's what kind of gives it such depth, both conceptually and technically. And I would like to explain, at least give you a flavor of some of these pieces by stating the theorems next. I'd like to now state Nash's theorems. Recall that our goal is to solve this system of nonlinear partial differential equations. The left-hand side of this equation describes the lengths measured in the ambient space RQ. The right-hand side describes the length that's given to us, the intrinsic notion of length given by the metric on the manifold. The solution to this system of partial differential equations actually gives us an immersion. In order to get an embedding, we must also insist that this mapping is one-to-one, but that's not a particularly important consideration for us at this point. The first theorem that Nash proved is in 1954. It's a short and absolutely beautiful paper. And in this paper, what he proves is that if we assume that the metric is C0, so the metric is assumed to be just a continuous function, and if we assume that the codimension is greater than or equal to 1, this is actually an improvement by Cooper of Nash's original work. Nash's original work had q greater than or equal to n plus 2. The statement of the theorem then is that under these assumptions, there is a C1 solution to this system of partial differential equations. There's another caveat, which is that one must make an assumption of the topology of the manifold, but that's a final point that is not actually, again, relevant for us at this stage. 2 years later, Nash proved a very different kind of theorem where the assumption on the metric is that it is C infinity. So we've changed the regularity from C0 to C infinity. And in order to get a C infinity metric, in order to get a C infinity embedding, one needs to improve the codimension from 1 to something which is order n squared. And in this setting, the statement of the theorem is that if we assume that the metric is C infinity, and the codimension or the ambient dimension Q is, let's say, much larger than n of order n squared, then in fact this equation has a C infinity solution. So just to kind of stress the way people think about this theorem over here should be thought about as low codimension, low regularity. This theorem over here is high codimension, high regularity. I would like to illustrate the striking nature of Nash's low codimension, low regularity result by presenting you with a simple example. So let us consider the embedding problem for the standard torus. So the standard torus is R2 quotiented by the integer lattice, and the notion of length is exactly flat Euclidean length. What we are trying to do is to kind of reconcile two pictures. On one hand, the torus defined intrinsically in this manner. On the other hand, the torus corresponding to, for example, the shape of a donut or a bagel for those of us who live on this continent. There are two theorems which should be contrasted with one another. On one hand, there's a classical result of Chern and Tompkins that says that there are no C2 isometric embeddings of the torus into R3. On the other hand, there is Nash's theorem that tells us there are infinitely many C1 embeddings of the torus into R3. So you see that the low regularity that is required in Nash's theorem is actually a sort of fundamental feature of the problem. And in fact, beautiful images of this particular embedding constructed largely by Nash's techniques and the sort of modifications due to Gromov can be found in this beautiful paper of Borelli and his co-workers in PNAS from 2012. To explain my viewpoint on the problems in this area, I would like to point out that there is a wonderful survey on Nash's work and its impact within mathematics. An entire issue of the Bulletin of the AMS in 2017 was dedicated to Nash's work. Articles in this issue of the Bulletin were written by leading figures in the area. So Misha Gromov discusses at great length the impact of Nash's work on geometry. Gromov expanded Nash's ideas into the H principle. His book from the 1980s, Partial Differential Relations, is basically his systematization of Nash's work. Kleinemann's article discusses another systematization of Nash's work with an analysis. So this was the work of Govind Moser and his students in the 1970s on what is now called Nash-Moser implicit function theorem. Kollard discusses Nash's work on real algebraic geometry, which actually preceded his work on differentiable manifolds. The article which is of most relevant to us, and in particular attracted me to this set of problems, is the work of Dilelis and Sekehidi. So what they did is to prove a rather striking result on the Euler equations of fluid mechanics. So that's a well-known difficult system of partial differential equations to analyze. And so what Dilelis and Sekehidi did is to adapt Nash's techniques, low codimension, low regularity, to construct counterintuitive solutions to the Euler equations. One of the things I would like to point out is that when one looks at the survey, there are certain words that do not appear in this entire issue of the bulletin. So the words information theory do not appear. And the word probability theory when it appears in a very superficial way. And so somehow the punchline of my work is that actually probability theory plays a rather central role in these problems. And that's basically what my formulation is about. Before introducing my probabilistic formulation of the problem, I would like to just explain where it came from. So one of the ways people have been trying to understand this problem is to try and distinguish between what we call rigidity and flexibility in terms of an understanding of critical exponents. So this can be illustrated with an example. Consider isometric embeddings of the sphere into R3. As we all know, if we just take the sphere, we can describe it as the solution set to the equation u squared equals 1. And a classical result asserts that this is the only possibility up to rigid motions. In fact, in the classical literature, the smoothness assumptions were not even kind of pinpointed because people just assumed that solutions to the differential equation must be twice differentiable. In contrast, Nash, by paying strict attention to the criterion of smoothness, established that if u is C1 and not C2, in fact, there are infinitely many solutions. So one can crumple the sphere, in fact, into an arbitrarily small ball around the origin in a way that an intrinsic observer on the here would not be able to tell the difference. So this is a very, very striking result, implicit in Nash's work. So one of the ways that one can try to kind of understand this problem is to seek a threshold that separates these two regimes. And one of the ways in which one can do it is by looking at a scale and asking if there's an exponent alpha that separates the regime of rigidity from the regime of flexibility. I would like to point out that the term critical exponent is very common in statistical physics. And in fact, when one views the connection with turbulence through the lens of statistical physics, it becomes apparent that this problem has some depth. My interest in this area was actually stimulated by exactly this question. The best known exponent in this area is that alpha is equal to 1.7. That is not optimal. I can't prove it yet, but I can say it's not optimal because it reduces in a very precise sense exactly to Nash's construction plus a new smoothing operation. And that's how I got started in this area. My goal was to bump up this exponent, but then it slowly led to something which is conceptual, though it began with a technical question. The main idea in Nash's proof in 1954 goes as follows, and it can be illustrated in a very simple model problem of embedding a circle.
Okay, maybe we are going to skip the end. Nobody.
But the problem is that the people connected, they are listening.
Oh.
That's the problem.
They can hear it?
Yes.
Oh, well, good for them.
The problem is he spoke too far away from the microphone. That's the problem.
Imagine shrinking all the lengths, since one can scale length in Euclidean space. And one scale length.
Try to explain to you, but I guess I'm not so qualified. But you can look online for the videos that was done for the flat torus. It's amazing. Done by French researcher.
Subsolution, one can always try to push up a subsolution towards the solution. And the way Nash does this is by adding in higher and higher frequency oscillations. So these high frequency oscillations are added in normal directions in a very, very clever and specific way. And what happens in this process is that one keeps adding in these fluctuations, and this is why the solution becomes rougher and rougher. And the key aspect of Nash's work is to show that as these subsolutions are getting rougher, they're getting rough in a controlled way. And so at the end, one still has a C1 solution to the differential equation. But a key idea is a discrete iteration and the addition of fluctuations. One of the questions that is stimulated by the connection between the isometric embedding problem and the work on turbulence is to ask if there are natural probability measures supported on isometric embeddings. So the central concern in turbulence is to find a rigorous explanation for the Kolmogorov universality. And one of the ways we would like to formalize that as mathematicians is to construct Gibbs measures which are supported on solutions to the Euler equations. So once one has seen the connection between turbulence and the embedding problem, even if it is at the level of technique, it becomes natural to actually go back to the embedding problem and to ask if one can import ideas from turbulence and apply them to the embedding problem. Another way in which application analysis of embedding problems is to ask if there is a unified approach to the embedding problem for finite metric spaces and metric graphs and the problem of embedding Riemannian manifolds. So over here, what we see is a connection between theoretical computer science and PDE, but these are traditionally treated as two separate bodies of technique. In fact, there's a very strong literature in this area. So the first application, the construction of Gibbs measures to the isometric embeddings, is precisely the way physicists formulate them. And in particular, my work in this area was deeply stimulated by Dan Frieden's work on the renormalization of the sigma models. It is also possible to just imagine the use of the embedding problem in Bayesian approach, for example, to computer vision. So while one would not apply things like, I think we all agree that handwriting recognition and character recognition are solved problems at the level of technology. If one adopts the Bayesian approach to these problems, then you see that one of the things that one has to do in the Bayesian approach to character recognition is to construct a prior
So I'll learn something on my laptop.
So for example, if you're trying to construct a prior on the letter O, you see that what you're really doing is just, when you're writing O on the blackboard, what you're really doing is
I don't want to do something I don't want to mess it up.
These questions are actually very, very natural, but there has been no prior attempt to address these dealing with the embedding problem,
what we will try in the replay, we'll try to include is recorded video into the replay, like cut the, and I hope that during the replay it will be better because people on Zoom, they hear it perfectly. Like it's low, but they hear it.
Discrete embedding problem. Then we relax the problem, and then we try to improve the relaxation to a true solution or a true embedding by adding in fluctuations. Now these fluctuations must be added in a very controlled manner. Let me illustrate the idea just with a simpler PDE than the embedding problem. So here, this is an example of an equation, iPhone equation, or a version of the iPhone equation. What I'm trying to do is to construct a random one Lipschitz functions. Here are examples of one Lipschitz functions. Here is an example of a subsolution, so just a smooth function whose slope is always less than 1. The way we will add in fluctuations stochastically is by adding on into the set of unknowns a reproducing kernel. So this idea comes from interpolating between Nash's work in 1954 and Nash's work in 1956. In the 1956 paper, what he does is he runs a continuous time evolution of not a subsolution, but a continuous time evolution of an approximation along with a smoothing operator. What I'm doing is I'm basically replacing the smoothing operator by a reproducing kernel and recognizing that it's possible to write out a closed evolution equation for both the subsolution and the reproducing kernel, which gives us a stochastic flow in the space of Gaussian measures. So the mean of the Gaussian measure evolves according to this equation. So this equation is an eco-SE, where we say that the covariance of the change in the subsolution is prescribed by L dot. And it turns out, so this really comes out of the Cameron-Martin theorem plus a modeling assumption, that the evolution equation for L dot must have this particular structure. So over here, one of the reasons I'm not showing you numerics is that this is still somewhat in play, because what one requires is a covariance kernel which depends in a natural way on the residual. And this turns out to be a little bit more delicate than I had expected at first sight. But two examples of choices that one can make are included in the written report, the article that comes, the article contained in conference proceedings. Let me give you a little bit more feeling for what the role of F is. So it turns out, and this really does parallel a lemma in Nash's paper in 1954, it turns out that when one replaces his fluctuations in the normal direction with the use of a covariance kernel, a replacement for one of his lemmas for the decomposition of metric is essentially this statement. So what I'm looking for is a covariance kernel such that if I sample Gaussian random fields that are drawn from this covariance kernel, then their gradients must match the correction, the desired correction. So it turns out that the structure of this problem is very similar to that of a semi-definite program. Some intuition for what's going on is the following. So what's really going on is that I've got a subsolution, and I'm adding in fluctuations at finer and finer scales, but in a controlled way of the subsolution. And at the physical level, one can think about this kind of joint evolution equation for the Gaussian measure described by this mean and that covariance kernel as a process of quasi-static equilibration. I prefer, rather than the physical integration, I prefer the Bayesian integration, which allows me to think about this problem as a process of measurement where I keep making optimal corrections in response to my measurements at the state t. So this allows us to see embedding as nothing but a process of replication, where I'm transferring information between a source and an observer. And the primary conjecture that I have in this area is that there should be no fundamental limits on embedding, except those which are implied by the channel coding theorem. That's very subtle to pin down, but this is a step in that direction. Thank you very much.
Wow.